So, good morning, all of you. Here we'll be starting. Good morning. We'll be starting the next part of this unit number 1, and as usual, there are only 70 people into the meeting. As I said, please join the class exactly at least at 11 o'clock, so that the basics will be covered. Further units will become easy if the first unit is, say, prepared properly. So without wasting time, I'll share my screen. So I have a PPT on my screen. Transfer function. Is it visible to all of you?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, thank you. So in earlier lecture, we have seen certain basic things of control system, classification of the control, I'll say systems for classification basically. Now the transfer function is, say, major part in this subject. The transfer function is nothing but it is ratio of output upon input. In control system language, if you talk, it is nothing but response to the excitation, is nothing but output upon input. So we'll talk about the transfer function here. Today, in today's lecture, the transfer function will be, say, somewhat we will see about transfer function, but later on in next successive lecture, we will be solving several problems on transfer function, and that will be available in university examination also. So moving ahead, we'll go through what is the transfer function. We'll see what is Laplace transform, means time domain means, what is frequency domain means, what is why transformation is required, what is Laplace transform, what is inverse Laplace transform. Quickly, even though you know what are different properties of Laplace and inverse Laplace, quickly we will go through that, and later on we will be working in S domain. So shortly I will introduce all this theory to you. So the transfer function is basically mathematical equivalent model of the system. As I said, I'm saying system, that doesn't mean it is electronics or electrical. It may be anything. It may be aeronautical, it may be say civil model, it may be mechanical, it may be electrical, electronics, or electromechanical, whatever. It may be human body. So mathematical equivalent of that particular system is nothing but a transfer function. The transfer function of the order of the transfer function represent the number of storage element or the number of time constant. This concept will be clear in further, say, PPTs. It is defined as the ratio of Laplace transform of output is nothing but response. Output is nothing but response to the Laplace transform of input. Input is nothing but excitation, under assumption of all the initial conditions are zero. There should not be any initial condition. Suppose we are talking about RLC circuit, and if there is an initial charge on capacitor, initial energy into the inductor, that should not be there. All the initial conditions are zero, like voltage, current, whatever, in case of, say, RLC circuit. Suppose in terms of block diagram, we can represent like this. U of t is the input, that is excitation. This is the system which is fed by an input. Then system will provide, as per whatever is the mathematical model, it will provide an output or response that is defined as y of t. As I mentioned, this y of t in certain book, it is defined or denoted by c of t, and u of t excitation is denoted by r of t, and transfer function is t of s. Okay, so we will be using these notations throughout the unit. So transfer function, here it is denoted by g of s, Laplace transform. S is S domain. We'll see what is S domain. Is nothing but Laplace transform of this y of t, which is in time domain, of course, y of t, divided by Laplace transform of u of t, this one. That is, of course, in time domain. So if we take the Laplace of the time domain, we get S domain form. So capital Y of S divided by capital U of S is nothing but the Laplace transform of output to the Laplace transform of input. At all initial condition are 0. So simply it is mentioned I1 is equal to 0. That is nothing but related to initial condition is equal to 0. We'll move further. We'll see what is the difference between time domain and frequency domain. Generally, whenever we talk time domain related to time and frequency domain is related to frequency, this is the short answer. Say few student always opt for. So we'll go in a detail what is difference between time domain and the frequency domain. The time domain graph shows how signal changes over time. For an example, sinusoidal signal. Frequency domain graph shows how much of this a signal lies within each frequency. Suppose we have a signal wherein we have several frequencies. So how many signals lies at say 1 kilohertz, how many signal lies at say 2 kilohertz, say 10 kilohertz, 1 megahertz, likewise. So number of frequency component at each frequency is denoted in, or this information is provided in the frequency domain. Coming to the time domain, in time domain graph, the magnitude x of t of the input signal at each time instant is represented. You know what is sinusoidal wave? Of course, this is the sinusoidal wave. It shows everywhere what is amplitude here, what is amplitude at say 0, what is at pi by 2, what is at pi, what is at 3 pi by 2, likewise. So at every instant we get the magnitude. What about the frequency domain? Signal is represented by sum of sinusoid of different frequencies, that is omega by f, each with certain magnitude, capital X of omega. So here what happen if I have 5 component of say 1 kilohertz frequency, so it will show you sum of all those 5 and its amplitude. And also if there is phase shift, so phase shift theta of each sinusoid is also recorded. Likewise, graph of frequency domain will be like this: 1 kilohertz पे इतने frequency, 2 kilohertz पे इतने frequency, 3 kilohertz पे say 0 frequency. So you'll get a frequency graph. So say we can say there are 3 component at 1 kilohertz, there are 2 component at 2 kilohertz, there are 0 component at 3 kilohertz. Same graph is shown in next PPT. So here is an example of time domain graph. Of course, as I mentioned, you are getting the amplitude at each instant is nothing but time domain at each instant t. So what is this signal? This signal is x of t in time domain, wherein you can see what is x of t. X of t is a sinusoidal of t plus pi by 3. If you see the equation, sinusoidal equation, it is a sine what omega t plus theta. So you can see this shows the phase shift, pi by 3 shows the phase shift. So there is one signal that is sine t plus pi by 3, and there is another, and what is magnitude? Magnitude is 1 here, and there is another signal that is 2 sine 2t. So 2 sine 2t, so it is here theta is not present, that means phase shift is not there. 2 is the magnitude and 2 is the omega. So here you can see there are 2 signals which are added together, and both are the sinusoidal waveform which are added together, and a graph shows like this. You can see there are up and downs. Addition kiya hai, somewhere the amplitude is less, somewhere it is negative, somewhere it is very high, because it is simply performing the addition of 2 sinusoidal waveform with different say attributes like different phase, different amplitude, different omega. So if I compute this using this formula, if I compute x of t at 0, then it comes 0.86. So it is somewhere here 0.86. If I compute at 6 pi by 6, then it is 2.73. So somewhere it is pi by 6, it will be 2.73. If at pi by 2, somewhere here, pi by 2 means somewhere here, so it will be 0.5. Okay. So similarly, complete signal is obtained. So time domain, you are getting what? Amplitude at each time instant t. Moving ahead, example of frequency domain, we have not changed the signal. Signal is same. This is just the format on the top corner of the PPT, like where A is the magnitude, A sine omega t plus theta. A is the magnitude, then omega is there, t is a time period, and theta is the phase shift. So there are two different frequency components. So these are separated now. X of t is sine of t plus pi by 3 plus 2 sine of 2t, has two frequency components. Of course, both the frequencies are different. So as shown in below. So here is one signal, sine of t plus pi by 3, wherein omega is 1, as it is t alone is there. So omega is 1. F is what? F, we will consider this is 1 by 2 pi, just for understanding purpose. And what is amplitude of omega? That is, it is x of omega is 1. Magnitude I'll say. Omega is 1 and x of omega means magnitude. Here sine के पहले 1 है. Similarly, in second signal, it is just 2 sine 2t. So in 2 sine 2t, omega is 2. You can see here, omega is 2 near to t. Then amplitude of this signal, that is x of omega, capital X of omega, is also 2. It is shown here. It is sinusoidal waveform. It is shown. Then theta, theta component है ही नहीं, 2t plus 0. Suppose 0 दिखाने की जरूरत नहीं. So theta, that means phase shift is 0. You can see this signal is starting at 0. Origin से start हो रहा है, that's why phase shift is 0. And you can see this signal is not starting at 0. This is starting somewhere here, somewhere here. Okay, so there is a pi by 3 phase shift here. Now these two different components are there in frequency domain. It is represented as shown below. Bottom में दो diagrams हैं. It is represented like that. So you can see x of omega is the magnitude, and here on y-axis there is a frequency plot. Just look at this. I'm interested in what the plot of number of frequencies. So at 1 by pi, so 1 by pi, if you put the value, you'll get magnitude 2. Two number of frequencies are available. Then here 1 by pi agar aap karoge, there will be two component present. Then 1 by 2 pi, 1 by 2 pi you have only one component present. And at 1 by 3 pi, there is 0 component present. So this is the frequency domain graph, and this is the phase. Second last one is the phase. On y-axis it is phase, and on x-axis it is what? Frequency. So you can see 1 by 2 pi, there is a phase shift of pi by 3, जो कि यहाँ पे दिखाया है. pi by 3 का phase shift अकेला ही यहाँ पे available है. So if you put this value into the equation, you will get this graph. Again at 1 by pi, there is no phase shift. 1 by pi ये यहाँ पे आ रहा है. 1 by pi there is no phase shift. 1 by 3 pi there is also no phase shift. So only one phase shift between these two, that is pi by 3, which is shown in the graph. So this, in this way, the frequency domain form is say represented. Now we'll go to the domain transformation. Several times we have to transform from time to frequency and frequency to time. So when to do this action? Of course, because in time domain we'll get certain information of the signal. In frequency domain we'll get some another information of the signal. So it is depending on your objective, what information you needed, accordingly the domain transformation step is taken. So same is given. It is somewhat theory type of points. A given signal of a function can be converted between time and frequency domains using mathematical transformation. Those will be learned later on. Fourier stated that any signal in time domain can be represented as a summation of sinusoid of different frequencies, that is frequency domain. Fourier series and Fourier transform we use for that. Then sinusoids are preferred because they do not change shape when passes through an LTI. LTI is what? Linear time invariant system. LTI is linear time invariant system, and in earlier lecture we have seen what is linear, what is time invariant, time variant we have seen. So linear means it follows the superposition and homogeneity. And what is time invariant? Time invariant means if I apply certain signal today, the output response, particular output response you will get. If you apply a signal tomorrow, you'll get similar response. You'll at any time, if you apply particular signal to the particular time invariant system, it gives you constant response. So any LTI system, and there can only be amplitude gain and phase shift. I'll explain this concept to you, like why the sinusoidal signal is preferred. You have seen several times during the practical, most of the circuit we use standard signal as a sinusoidal signal. We apply sinusoidal signal and we test the performance of particular circuit, because sinusoidal signal अगर LTI system से pass हो रहा है, so output में इसका shape change नहीं होता, it remains same. The shape of the sinusoidal will remain same through LTI system. Only what changes? Its amplitude may change, its phase shift may change. Like very simple example of RC phase shift circuit that you already performed in the lab. If I passes in input say RC phase shift circuit को अगर single pair है RC का suppose, if I connect input sinusoidal waveform, then output is also sinusoidal waveform, but there will be a change in magnitude and phase shift of ideally 60 degree between input and output you will get. But if you provide DC signal, that is step input to RC circuit, then what happens? You will get charging of the capacitor, that is exponential of the capacitor. Exponential signal you will get. Sakshi Verma, are you attending the lecture? Sakshi, Sakshi Verma, talk to me.
Yes, sir. Yes, sir.
So what is this disturbance? Why you are turning on your mic?
Sorry, sir.
This should not happen. It is disturbance to the lecture. Okay. So this is how sinusoidal are preferred through LTI system, because they do not change its shape. It changes only amplitude and the phase. Okay. So next is advantage of domain transformation. So each domain of signal representation provide us with different kind of information of the same signal. As I mentioned, if I go for the time domain for particular signal, as I explained earlier, example लिया था हमने x of t sin of t plus pi by 3 plus 2 sin of 2t. So in that, this is in time domain. What we got amplitude at each instant time t. But as we went for frequency domain graph for that, so we got there are two frequency component at pi 1 by pi by 2 pe. We have only one frequency component 1 by pi by 1 by 3 pi pe, it is 0. So signal is same but providing you different information, and phase shift also different information in time domain and frequency domain. So, कोई भी domain में जाओ, you'll get certain information. Depending on the objective, आपको क्या करना है, आपको कौन से चीज का analysis करना है. Objective analysis in one domain is advantageous over analysis in another domain. For example, signal having characteristic that changes with frequency. Okay. If I change frequency, signal का characteristic change हो रहा है, can be easily analyzed in frequency domains, of course, as compared to टाइम डोमेन, क्योंकि टाइम डोमेन में फ्रीक्वेंसी में क्या चेंजेस हो रहे हैं वी कैनॉट easily identify. So domain transformation is completely dependent on your objective and analysis. Okay, now next, this is the theory of say time domain, frequency domain, their advantage, disadvantage, when to do what transformation, such say little idea of domain transformation. Now moving to the Laplace transform. Okay, what happening here, all the students, I'm going through the PPT continuously. If you have any say query or any doubt, you can interrupt me at any time. Okay, because as you are not in front of me, I cannot see your faces, and accordingly I cannot decide whether you are getting the things or not. So if you have any doubt, any queries, you can interrupt me at any time instant. Okay. So Laplace transform, most of you are known to Laplace and inverse Laplace in mathematics. Laplace transform. Now, motivation, Laplace transform क्यों है? Consider the model of unforced mass spring damper. Now this is new to you. Mass spring damper. It is actually mechanical system that will be covered later into the unit number 1 in detail. Just for this time, you just focus on the equation, not the analysis. Mass spring damper is a mechanical thing. System has certain equation, that is mx double dot, double derivative of course, bx dot plus kx is equal to 0. This is the characteristic equation of one of the mechanical system where we have mass, spring and damper. Damper is a kind of friction or opposition to the force, and mass and spring generally provides you the oscillation. Then solution to this equation correlate कैसे करते हैं हम, देखो इलेक्ट्रॉनिक्स से आगे भी पढ़ने वाले हैं. इज ऑफ द फॉर्म x ऑफ टी, या वो इक्वेशन कौन से फॉर्म में है बोले, x ऑफ टी इज इक्वल टू e रेस टू पावर माइनस सिग्मा टी into a sin omega t plus theta. Don't go in detail, just I will tell you the relation. A sin omega t theta is nothing but sinusoidal, means oscillation, that is due to the mass and spring. Unfold mass and spring, this will provide you the oscillation. That's why it is represented by a sin omega theta. And if damper is present, if damper is not present, suppose if I remove this component b of bx dot is suppose 0, then the equation only will be x of t equal to only a sin omega t plus theta. But if this damper is present, damper is nothing but opposition to the force, it is kind of resistance. If damper is present, b of bx dot is present, then it will be represented by say exponential term, that is e raised to power minus sigma t. That is, the displacement x of t can have two component, exponential and sinusoidal term. Okay, so the graphical representation is on the same PPT. Exponential term is due to damper. As I said, it is opposition to the force, while sinusoidal term is due to interconnection between mass and spring. Oscillation provides करते हैं. So these two signals are together, you can see on the PPT, that is e raised to power minus 2t. You can see it is the exponential graph going towards 0, having certain magnitude 1 and going towards 0 at certain time, say somewhere here 14 pe. And another is sin t. Sin t is a sinusoidal signal as shown in the diagram. And what is done? These two are added, you can see, into the characteristic equation. Let me clear the screen. You can see added, right? So if we get the response of these two signal, what happened? This becomes damped oscillation. It will have certain energy and it will goes to 0 at certain time, because what is happening here we are using exponential and sinusoidal term together. So you'll get this separate signal जो हमने यहाँ पे देखे हैं पहले ग्राफ में, if they are combined like x of t equal to e raised to power minus 2t into sin t, it will be underdamped oscillation you'll get. Okay. नेक्स्ट Laplace transform की जरूरत है, motivation. It is observed that solution to differential equation of LTI system are either exponential or sinusoidal or combination. Differential equation में ये सब रहता है, exponent, sinusoidal or combination of that. In frequency domain transformation, the signal are decomposed into sinusoids described by amplitude and phase at each frequency. To account for exponential response as well, we extend idea of frequency domain representation. A new transformation is defined such that the signal are decomposed into both sinusoids and exponential. ये दोनों को हमें decompose करना है simplest form में. So new transformation is defined. That is nothing but Laplace transform. Decomposes signal in time domain into a domain of both sine and exponential. Domain of the Laplace function is called S domain. Laplace function को S domain इसीलिए हम S लिखते हैं, V of S, Y of S. So S domain, S stand for Simon. He has invented this Simon domain. S is the complex number. That is, S plane is two-dimensional. One dimension is to describe frequency of the sine wave, that is omega, and another dimension is to describe the exponential term, that is sigma. And pattern will be, of course, form will be S is equal to sigma plus j omega. So given S, we can get an exponential sinusoidal as, that is, e raised to power st will be equal to e raised to power s के जगह पे पुट किया है sigma plus j omega, so sigma plus j omega into t, so it can be written like this, e raised to power sigma t in bracket j omega जो convert होता है, that will be cos omega t plus j omega t. So let's see the definition of Laplace transform. Given a signal x of t, which is in time domain, of course, its Laplace transform is given by L of x of t represented by capital X of s. Laplace transform is represented with capital X of s, will be integral of 0 to t x of t, that is signal in time domain, of course, into e raised to power minus st into dt. So this is how is the definition, where L is the Laplace operator. Existence of Laplace transform depends on the coverage of an integral in equation 1, which depends on the value of sigma. The region in S plane in which Laplace transform exists for a function x of t is called region of coverage. We'll go in detail regarding this region of coverage later on. So this is the definition of Laplace transform. Now the example. Very simple example is quoted here. Say example 1. Find the Laplace transform of x of t is delta t. What is delta t? Delta t is nothing but impulse function. It is infinite at 0 and in minus infinity towards minus infinity and plus infinity it is 0. So here Laplace transform of given signal, that is delta t x of t, it is represented by x of s is equal to 0 to infinity, putting into the definition delta t e raised to power minus st dt. So solving this, of course this value is 1. Solving this you will get e raised to power minus st, क्योंकि ये वाला 1 है, delta t is 1. So e raised to power minus st at t is equal to 0, it is e raised to power 0 is equal to 1. Another example, find the Laplace transform of x of t exponent के लिए, exponential, that is e raised to power at. So exponential form, you should know the mathematics for this. You please practice for say Laplace, inverse Laplace, then derivative integration, partial fraction, complex number, and so on. So इसका लिया है Laplace transform represented by x of s and definition में put किया है x of t के जगह पे it is e raised to power minus at into e raised to power minus st dt. So e raised to power minus at का डिफरेंस इंटीग्रेशन हुआ है 0 to infinity लिमिट के लिए. It is e raised to power minus s plus a into t divided by minus s plus a 0 to infinity. After putting this limit, you'll get 1 upon s plus a. For what? For this exponential function. Impulse function के लिए क्या मिला है? 1. Exponential function के लिए क्या मिला है? 1 upon s plus 1. This is the condition for ROC. We'll see it in detail later on. That is s plus a should be greater than 0. Of course, if s plus a is less than 0, there will be a problem. Then sigma plus a should be greater than 0 and sigma should be greater than minus a. This is condition for region of covariance. Third example, find a Laplace transform of x of t is equal to t. So definition में put करना है x of s is equal to t into e raised to power minus st, 0 to infinity integral of course dt. So it can be solved by integration by part rule. So a to b u dv is equal to uv a to b minus integral of a to b u du. Okay. So where u is what? U is nothing but t. इसका first term. What is v? V is minus 1 by s e raised to power st. Putting into the equation, putting into this equation, we'll get x of s का t का ये function जो है x of t is equal to t, इसका transfer function मिला है हमें 1 by s square by putting of course the limit into this part. 1 by s square. Okay, it is okay if x of t is equal to t, t means it is t to the power 1. If there is some order to the t, that is say t square, t cube likewise, then if you solve this, then x of s is n factorial divided by s to the power n plus 1. Now you might be thinking, do I need to derive, say, compute this Laplace transform for each and every signal? Of course not. You have to logically remember this. Like somebody is saying that transfer function of impulse signal is what? It is 1. What is transfer function of, say, exponential functional e raised to power minus 2t? ऐसे अगर दिया है, what is transfer function of e raised to power minus 2t? Then you have to directly say that it will be 1 upon s plus 2. Okay, so no need to actually do this action. So third example, similarly fourth example, एक sinusoidal signal लिया है x of t is equal to sine of at, kept into the definition of Laplace transform. Then it is solved. Later on, finally, for sinusoidal waveform, what we get? We get, it is sine omega t. We get omega upon s square plus omega square. You can see a upon s square plus a square. Similarly, if we go for the cos signal, then it will be s upon s square plus a square, or say you can say s upon s square plus omega square. So similarly, we have gone through certain examples how the Laplace transformation is done for unit impulse response, then for sine, cos, then t, that is step input. So here I have quoted everything. Unit impulse के लिए delta t है, Laplace transform is 1. This is unit impulse की diagram. If it is a constant value, अगर Laplace transform of 2 निकालना है आपको 2, so Laplace transform of 2 will be 2 by s. Then step of a at t is equal to 0, that is a u of t is a step input. So this is the magnitude a step input. It will be a by s. Quickly, I will go through that. Putting into the definition, this has been calculated. Delayed step means what? AU of t था, अभी AU of t minus t है. ये जो सिग्नल यहाँ पे स्टार्ट हो रहा था 0 पे, it is started at t. So it is written that is a divided by s into e raised to power minus t s. This is the Laplace transform. RAM के लिए, this is the RAM signal. A of t is the RAM signal, is nothing but a upon s square. Please don't get confused between these two. For constant value a, that is a upon s, and for RAM it is a upon s square. Delayed RAM means RAM यहाँ पे 0 पे चालू नहीं हुआ, it is started at say t, then it will be a of t minus t, that will be a upon s square into e raised to power minus t. Whenever it is say delayed, you can see the exponential term is there wherever it is delayed. Please turn off the mic. Aishwarya Patil. Aishwarya Patil. Okay. Similarly, for parabola, that is at square by 2, like this, we have a divided by s cube. Exponential decay, e raised to power minus at, it will be 1 upon s plus a. ये हमने निकाला है, I hope we solved this. Then time polynomial, that is t raised to power n, it will be n factorial divided by s to the power s plus 1, n plus 1, sorry. For sinusoidal, this is the sine waveform. It is omega upon s square plus omega square. For cosine, it is s upon s square plus omega square. You have to directly use this function. Damped sine, you can see sine wave जो है वो damped है. Damped sine means हमने इससे पहले ही एक एग्जांपल लिया है, exponential term into sinusoidal wave, that is the underdamped sine wave. So e raised to power minus at into sine wave, you can see here it is omega. Sine wave का फॉर्मूला ये देखो, Laplace transform क्या है, only for sine wave it is omega upon s square plus omega square. So जो भी हमें exponent में term है a, that has to be added with s. So here omega upon s plus a whole square plus omega square. For similarly for damped cosine, e raised to power at cos omega t, that will be s plus a. s के साथ a यहाँ का जो है exponent का ये part t के पहले का ये join कर देना है, s plus a upon s plus a whole square plus omega square. So these are the some important signals wherein the Laplace transform are computed, and you may use these say directly while solving the transfer function. No need to put into the definition and convert, say compute the Laplace transform. Now what are the properties of Laplace transform? Finding the Laplace transform of x of t, which is in time domain of course, following the basic definition is cumbersome in many cases. Of course, definition कितना danger है? It is x of s is equal to integral of 0 to infinity x of t into e raised to power minus t dt. And x of t जो है अब तक जो हमने देखा है, those are very simple. T raised to power n, then constant, then e raised to power at, then sine, cos. We have seen, then RAM, exponential. But sometime if x of x is very, say, complex, then solving the Laplace transform, putting into the definition will be somewhat cumbersome. Then to simplify the process, certain properties of the Laplace transform have been derived. You may, of course, you may have learned the properties of Laplace transform. Why those properties are there? Sometime putting x of t into the definition and solving it, it is quite difficult. So to simplify that, some properties are defined. In practice, Laplace transform are obtained by the application of one or more of these derived properties. Quickly we'll go through the properties because it is already covered into mathematics subject, but recall karna zaruri hai, and because we have to use while solving for transfer function in the coming numericals. Now, properties of Laplace transform. First property is very simple. It is straightforward. That is linearity property. I have one signal x1 of t whose Laplace transform is x1, capital X1 of s. I have another signal x2 of t. Laplace transform is x2 of s. Then if I say add a constant to x1 and x2, if my signal is ax1 of t plus bx2 of t, then I may write a into Laplace transform of x of t, that is x1 of s plus b into x1 of x2 of s. So this is what linearity property. Time shifting property. If x of t Laplace transform is x of s, then if I change the time, that is x of t minus t0, then Laplace transform में क्या होगा? Time shifting property में it will be e raised to power minus s t0 into x of s. ये जो निकल रहा है इसके साथ ये e raised to power minus s t0 हम लिख सकते हैं. That is time shifting. Quickly we'll go through. Time scaling property. If this is the signal, I'll not talk every time. हर एक इसमें x of t का Laplace transform x of s ही है. So टाइम स्केलिंग मैंने क्या किया, a के t के साथ टाइम स्केलिंग कर दिया है, एक कांस्टेंट लगा दिया. सो x of at will be what? 1 by mod of a into x of as. टाइम रिवर्सल प्रॉपर्टी, x of t है, वेरी स्ट्रेट फॉरवर्ड. x of minus t अगर कर रहे हो तो इट विल बी x of minus s. Then time differentiation property. This is the say function x of t is equal to x of s. Time differentiation, what I did, I derivated x of t with respect to time. Then the Laplace transform will be s into x of s minus x of 0, where x of 0 will be the initial condition. Then double derivative अगर लिया मैंने for x of t, it will be s square into x of s, and initial condition s into x of 0, x dash into x of 0. As and when we will use, it will be more clear. Time integration property, integration किया है x of t को, then it will be 1 by s. You can see differentiation में s multiplication में जा रहा है, Laplace transform x of s के यहाँ पे division में 1 by s into x of s. Frequency differentiation property, if x of t Laplace transform is x of s, then t into x of t, that is frequency differentiation, will be d by ds. with respect to s हम differentiate कर सकते हैं x of s को. If there is a order, that is t raised to power n x of t, then it will be minus 1 to the power n into dn by ds to the power n x of s. Like for an example, it is t square. Suppose t square x of t, what it will be? It will be minus 1 square into d square by ds square into x of s. Then frequency integration property, this is common form, x of t is equal to x of s. Frequency integration कैसे है? We are dividing x of t by t, so it will be integral of s to infinity x u du. So these are certain properties. Frequency shifting, so x of t is equal to x of s. So frequency shift किया है e raised to power s0 t into x of t. So we may write x of s minus s0, and this is the periodic function. Rarely it will be used in, say, here. So Laplace transformation of piecewise periodic function f of t with period p is given by x of s is equal to 1 over 1 minus e raised to power ps 0 to p e raised to power minus st into x of t dt. So these are all property. Along with this, there is a initial value theorem and final value theorem. We'll be using this theorem while solving the problem, of course. So This initial value theorem relates the S domain expression to the time domain behavior as time approaches to 0. So you can see limit x time approaches to 0, t is equal to 0. Laplace transform is limit s x of s where s tends to infinity. For an example, here I have a signal 3 plus 4 cos t, 3 plus 4 cos 2 t. Then I kept the limit t is equal to 0. So putting this value, you will get what? That is 3 plus 4 is equal to 7. Now coming to the S domain, time domain में क्या आया? Limit put करने के बाद 7. Coming to the S domain, limit s x of s tends to infinity. So limit s tends to infinity, s into 3 by s. क्या किया इसका लैपलास ट्रांसफॉर्म लिया है. 3 इज अ कांस्टेंट, 3 का लैपलास ट्रांसफॉर्म क्या आता है? अभी हमने देखा है 3 by s. cos का लैपलास ट्रांसफॉर्म क्या आता है? cos ओमेगा t. इट विल बी ओमेगा अपॉन s स्क्वायर प्लस ओमेगा. ओमेगा क्या है यहाँ पे? लेट मी क्लियर द हाइलाइट्स. यहाँ पे ओमेगा क्या है? cos st में ओमेगा इज 1, 4 is a constant. So you can see here 4s divided by s square into 1 का स्क्वायर 1 ही रहता है. So it is cos का Laplace transform s upon s square plus omega square. So I have 4s upon s square plus 1. लिमिट पुट किया है मैंने, इन्फिनिटी रखा है s के जगह पे पूरे. So it is 3, it is 4 into sorry यहाँ पे इन्फिनिटी जो है, पुटिंग द लिमिट इन्फिनिटी इट विल बी 1 प्लस थोड़ा एडजस्टमेंट किया है 1 प्लस 1 अपॉन एस स्क्वायर और बाद में लिमिट पुट किया है तो एस स्क्वायर इज व्हाट? यहाँ पे इन्फिनिटी पुट करोगे सो दिस टर्म विल बी 0. सो 4 by 1, so 3 plus 4 again it is 7. So you can see initial value theorem. Initial value theorem क्या बताता है सीधे सीधे? If in time domain t tends to 0, s tends to infinity. That's it. So note, initial value theorem is applicable only in cases where Laplace transform exists and its limit exists to s tends to infinity. Similarly, we have reverse, that is a final value theorem. It relates the s domain expression to the time domain behavior as approaches to infinity. That is, time approaches to infinity, s to the 0. उल्टा करना है. For an example, I have 1 minus e raised to power 2t divided by 2. So putting t is equal to infinity, e raised to power infinity, that becomes 0. So you can see here 1 plus 0 divided by 2, it is 1 by 2. Let's go into the Laplace transform. Laplace transform निकालने x of t जो है इसका Laplace transform निकालने से पहले separate it. So it will be 1 by 2, 1 by 2 and minus it will be e raised to power minus 2t divided by 2. You may take 2 common, okay, later on. So 1 by 2 का क्या है? 2 अगर कॉमन बाहर निकल गया तो 1 का क्या है? 1 का लाप्लास ट्रांसफॉर्म इज 1 by s. and what is e raised to power 2? ये वाला ये लाप्लास ट्रांसफॉर्म है 1 by 1 कांस्टेंट 1 वैल्यू का. एंड e raised to power minus 2t का क्या है लाप्लास ट्रांसफॉर्म? इट इज 1 upon s plus 2. और ये जो है ये 2 और ये बाहर निकाला हुआ है हमने. सो नाउ हियर लिमिट हमने t tends to infinity, so s tends to 0. लिमिट 0 पुट करने के बाद it is again half. You can see these value are same, but the action is reverse. If time is 0, then s is infinity. If time is infinity, s is 0. So final value is applicable only in cases where Laplace transform exists and its limit as s is equal to 0. Also final value should also exist. So this is all about the properties and theorem of the Laplace transform. If you have any question, I'll spare 1 or 2 minutes with you related to question, if any.
I was like,
Sakshi, Sakshi, your voice is very. Hello, Sakshi, your voice is very say noisy. Nothing is say audible. Do you have any question? Please raise your hand. Mic by mistake on हुआ है या you have any question? If you have any question, please raise your hand. Nobody has question. Very good.
हेलो सर।
Yes, Revati.
सर आपने एक क्वेश्चन लिया था, मतलब एग्जांपल बताया था, ई रेस टू पावर सम एस ऑफ टी इनटू साइन वाला एक एग्जांपल था। तो सर उसके अंदर
E raised to power.
मतलब एक्सपोनेंशियल फंक्शन और साइन फंक्शन का ये था, लैप्लास वाले।
Example.
हाँ, तो सर उसके अंदर मतलब अगर साइन जो है उसके लिए हम
हाँ.
लोग हमेशा मतलब मेरे हिसाब से वहाँ पर नेगेटिव साइन चाहिए था, आपने पॉजिटिव दिया, क्योंकि अगर उसका मतलब जो साइन फंक्शन है
Okay, okay.
उसको पहले उसको रखना पड़ेगा एक्सपोनेंशियल।
It may happen while preparing the PPT. Let me go to that slide. Is it visible? Tell me. This one. Example. This one. Am I audible? Is this the example?
No sir, it is exponential and sine.
It is before properties or exponential and sine. जो वेवफॉर्म वाला बताया था वो.
This one.
This one. Okay. What is query? It is sine of 80. So it is x of s, sine of 80 e raised to power minus st. Then I'll say this is a step 1, step 2, step 3, step 4, step 5, step 6 and step 7. Where is the problem?
Step 2.
Step 2 means here.
Yes sir, ते वहाँ पे ऐसे चाहिए e raised to power j80 minus e raised to power minus j80 by 2j.
This one.
Yes sir.
This me. It's everywhere. Yes. Yes, of course. It must be minus. Sometime while typing into the PPT, it happens. No. So it is minus. So it will be again minus here. So minus. Okay. I'll do the corrections. I'll look into the book. I'll do the correction. Accordingly, I'll post the related notes on Teams. Thank you for correction. Any other query?
No sir.
Okay. All of you actually say teaching into the classroom and teaching online is very different, because say preparing for half an hour lecture, it needs near about 2-3 hours to make PPTs. So sometime it happens, some notations may be different, some say polarities may be different, कुछ पैरामीटर लिखना ही बाकी रह जाता है, कॉपी पेस्ट करते वक्त भी वैसे होता है, like some equations are repeated on say earlier PPT, so I copy it and paste it on next PPT. So sometime there might be say some queries or say mistakes. So you please point of view, all of you can point me the whatever is the mistake on the PPT. Okay, so no worry about that. So I'll correct it and later on I will post it into the Teams. I have already posted the lecture 1 PPTs on Teams, and I have shared the link on SharePoint links on your WhatsApp group. I hope everybody got that. Okay. So if there is no question from your side, I'll once download the attendance and later on I will disconnect this meeting. Okay, no questions. So thank you very much. Bye.